So my talk is not about implicit biases. It's about the distinction between explicit and explicit representations. So it's a slightly different topic. And just to set the scene, in my whole career I have been concerned with the question of how to explain the human conceptual repertoire. So we're the only animals that can think the unlimited number of thoughts we can think, formulated over 500,000 different concepts in English, most of which no animal represents. And as a matter of logic, accounting for the human conceptual repertoire will involve characterizing the innate primitives, characterizing the adult repertoire, what's our target, asking whether there are discontinuities. I mean, is the innate state really different, initial state really different from the adult state? And insofar as they are, specifying what kind of learning mechanisms can underlie those discontinuities. This is just a matter of logic, but that leaves open the question, all the questions that are debated in the history of philosophy and the history of psychology. How rich are the innate primitives? Does it make sense for there to be discontinuities? Are there learning mechanisms that can realize discontinuities? I'm going to talk about core cognition, that's the innate state, and give you a feel for the claim and the evidence that contrary to the British empiricists, contrary to associationists, the initial state of infants include structured innate representations very rich with abstract content. And these are identified, the entities that fall under those representations are supported by innate perceptual input analyzers. It wouldn't do any good to have innate concepts with innate conceptual role if you couldn't recognize when you were in the presence of an entity that fell under that. And there's an innate central inferential role. So that's just a positive claim about what the initial state is like. So I'm going to give some examples and raise a puzzle. So the attested domains of core cognition are object representations and the physical interactions among them, causal knowledge about object representations, knowledge of agents and intentional agency. I'm going to just mention some of the research and give you a sense of how abstract and rich this is, and number. So I will talk about number because there I'm going to distinguish a few ways in which knowledge could be implicit. But let me do agency first. So there is very, very good evidence that babies represent the actions of other agents as goal-directed. And here's a sample kind of experiment. You habituate the baby to a hand reaching out and grabbing an object. So the baby gets bored with that. Then, after the baby's bored with seeing you reach for the same object all the time, you switch the objects around, and now either the hand does the same motion it did before, but now it's reaching for a different object, or it reaches for the same old object in a new place. And the logic behind this is if they represented the goal of that reach as being the ball, they should see this as the same thing that they just got bored with, and they should recover their interest in this case. And that's what happens. From 5 months on, they recover their interest in this case. And you can, under some circumstances, get 3-month-olds to do that as well. Now, so there's a very long story to rule out deflationary alternatives of this behavior. If you want to ask me questions, in the question and answer period, I'll tell you how people address those. But what I want to show you is how rich the system of representation of agents is. It turns out in this experiment, it's important that there's 2 objects there. If it's only the ball that you're reaching for, the first time you introduce the bear, the baby has no prediction about what you're going to reach for, and that's quite rational because here you've essentially shown the baby that the agent prefers the ball to the bear. When they've never seen the bear before, how do you know which one they're going to prefer. So at 5 months, as soon as they can do this, it's actually a preference they're tracking, not just a goal, or the preference enables them to establish what the goal is. So as soon as they do that task at all, the question is, well, what other information is integrated into these predictions? So I'm going to show you that the baby's representation of perceptual access, whether the person can see that object, determines whether they represent it as a preference. So this is the same kind of experiment. So the person is reaching for one of them, right, over and over again, right? But in some cases, the other one that they don't prefer is blocked from this person, not here. This person can see this one, but in the middle one, the person can't see that box there, and in the one over there, they can again because the box is higher, okay? So there's screens, but in the middle one, if the child can analyze the relation of seeing there, then in this case, although the baby can see both of them, the baby should not see the person as making a preference.
The cord to your computer is going exactly there, so you don't pull it.
I'm fine. Yeah. So in that case, the baby should not attribute a preference to that person because the person can't see both of them. And so what happens? In which of these conditions is the baby surprised when she now reaches for the other one? In the two where the baby can infer that the agent can see them, but not in the middle one. Okay? So as soon as the baby can impute a preference, the baby is taking into account the sort of perceptual access that the agent has. And of course, the gorgeous and interesting experiment is this extends to false beliefs in prelinguistic babies. There's a famous Onishi and Bailargian study where the agent puts, I don't know why it was a watermelon slice in one of those boxes and then reaches into that box. So that's what the baby is familiarized, reaching repeatedly into the box into which that person put the watermelon slice. And then there are 4 conditions. In one of the box moves. So it's again, the person put it in the green box, the dark box there. In the true belief green condition, one of the boxes moves, then there's no reason to think that the watermelon isn't where you left it. Here's a case where the watermelon goes from the green box to the yellow box, but the person sees it. So now the person should have a true belief it's in the yellow box. And then you just close up the back so the person can't see it move. And so now the person should have a false belief that it's still in the green box because they didn't see it move. And here's one where they see it move to the yellow, then it goes up and then it moves back. So now they should have a false belief that it's in the yellow box. Now the question is, what does the person predict? What does the baby predict? Where does she predict the person is going to search for the object? And the answer is they based on the belief of the agent, not where the baby knows it to be. Okay, so the conclusions from this, I mean, this is a lightning summary of hundreds of experiments. The conclusions are, infants represent goal-directed actions of agents as such, tracking perceptual, attentional states, even epistemic states, and tracking environmental constraints. So I haven't shown you these data. So if you're reaching for something over here and there is a barrier, and you reach like this, that's perfectly sensible because the child takes into account why you're reaching like this. You then take that barrier away. The child is surprised if you keep doing this, even though that's what they got bored with. They expect you to do this. So this is subject to I'm just trying to show you how structured, how complex, how much is being integrated into these predictions here So they track environmental constraints, predicting the agents will perform the most efficient actions to achieve their goals. Okay, so this illustrates innate representations with abstract content, goal, attentional state, epistemic states, environmental constraints. How does the baby identify goal-directed action? Well, there's multiple mechanisms. It's just too important to have only one input analyzer. They have an innate representation of what agents look like. They have a face schema, eye schemas, and if you can do this with geometrical figures, you put eyes on them and they're more likely to do goal-directed things. But they can also do it by just analyzing the action. They're sensitive to self-generated motion, but most importantly, equifinal approaches to a goal and sensitivity to the environmental constraints. So the action of a geometric figure in an array is itself input to whether you attribute goals here, okay? So that's just an example of core cognition. Here's the puzzle. Children cannot answer where will the agent look for the object until age 4, when you actually ask them the question. But notice, what they're predicting here is where the agent will look for the object. It wouldn't be surprising if children can't answer the question, where does the agent think the ball is or the watermelon is, because that requires knowing think, right? But here, the question they can't answer is exactly the same question, namely prediction. Where will they look? Where will they reach for it? They do not do this till age 4. Similarly, in core cognition of objects, one of the core constraints is what's known as a solidity constraint. So if you put a shelf across the whole table, enclose it in a box with an open top, cover the top, and drop something, 2-month-old babies expect the thing that you've dropped to be on top of the shelf and not under the shelf, right? That's just reasoning about the solidity constraint. That object can't pass through the space occupied by another solid object. At age 3, you do exactly the same experiment. You drop it and you just ask the child to point to where the object is. They're at chance, okay? And similarly, I'm going to show you for number. So the question is, how can babies be so smart and how can 3-year-olds be so stupid? And one response is core cognition is implicit, right? So core cognition differs from the kind of cognition that the child has to draw on to answer a question posed in language. And here, the distinction between implicit and explicit is one that many people have alluded to here. Implicit is not accessible or not verbalizable, and explicit is accessible or expressible in language. Now, what I'm going to argue is that there's another distinction we might have in mind between implicit and explicit. And I think it's going to do more work for us than this one. I mean, I don't find this as an explanation for the failure as illuminating at all until you have an analysis of explicit and implicit and some independent way of showing that core cognition is implicit. This just seems to be renaming the phenomenon. But it is a move that's made in this literature. Okay, so what's the more useful distinction between explicit and implicit? Okay. So I said I'm going to be talking about implicit and explicit mental representations. This should be called mental representation. And by this I mean the commitment we have as cognitive scientists who accept a computational representational theory of mind. We are committed to there being mental symbols in the mind. This is not a metaphor. This is dead literal, okay? This is a central theoretical construct in some branches of modern cognitive science. And if there are symbols in the mind, then there have to be answers to the question of what gives those symbols their content, what determines what they refer to, what gives them the meaning they have. what are they like? What's their format, right? Are they picture-like? Are they strings of 0 and 1s? Are they analog symbols? Are they discrete language-like symbols? And how does that format support the computational processes, the computational role those symbols enter into? We are committed to there being answers to that question and those questions, and we actually try to study that. That's the work of cognitive psychology. And so what I want to do now is race through the evidence for two more systems of core cognition, two different systems of core cognition with numerical content, to show you how we answer those questions about a system of representation, and after which we can say what's explicit and what's implicit, right? So this is what we're looking for if we're going to talk about innate logic, right? So core system 1 is an analog magnitude system. These are representations of approximate cardinal values of large sets of individuals. And I want to show you that you have them, okay? So I'm going to do this by flashing four sets of dots. And I need you to yell out so you can hear each other, so you can see the phenomenon. How many dots there are on each slide. So ready? How many?
16.
Sorry.
20. 18.
Okay. Now this is doing this automatically going forward. I don't know why. It was 16, 8, 32, 24. Now, if I had calibrated you, so if I had shown you what 100 dots is, the average you would have given would have been 16, 8, 32, 24. Okay? Now you're not counting, you didn't have time to count, and I can, if I just do it for 250 milliseconds, I know you don't have time to count. Your estimates are still as accurate. This means you have some way of apprehending, of representing the numerosity of those dots. You've also mapped them to verbal numerals, but I'm doing that. I just don't want it to go forward. You've mapped them to verbal numerals, but the important thing is you have a non-linguistic system that essentially creates representations of the cardinal values of sets. Now, what do I mean by it's approximate? I hope you saw that for 8, I heard 8 and 10. For this one, I heard everything from 20 to 50, right? That is the signature of analog magnitude representations of number. Sensitivity is a function of Weber's law. There's more noise the bigger the absolute value of the quantity you're estimating. This is a system of representation that we use to represent all kinds of continuous dimensions like loudness, brightness, area, length, but also apparently we can take sets of individuals and get a numerical representation. Okay, so here's how this system works. Number is represented by a quantity that's linearly or logarithmically related to the cardinal value of the set. So here's an external analog magnitude where length is the symbol. And these are, I've made the lengths linear functions. I just want to show you Weber's law, right? So it's much harder to discriminate 7 and 8 than 1 and 2. It's because discriminability is strictly a function of ratio and nothing else in the system. And that's how these number representation works. And that babies have these, rats have these, pigeons have these, and you have them. So this is continuous through development. And it's evolutionarily ancient. And this system of representation supports a whole variety of numerical computations. Using this system of representations, you can add, subtract, compute ratios, divide, multiply, compare cardinal values of sets. That's another reason we know these are number representations, that they support all kinds of number-relevant computations in animals and in babies. Okay? So this is implicit in the sense of not accessible. Until I showed you this, you probably didn't know you had analog magnitude representations. So you are not aware in any, you're aware of apprehending a set of dots, but you're not aware that of the nature of this representational system. Okay. Here is a second system. Here is a task, different task. The baby watches while you put 1, 2, 3 crackers in one bucket and 1, 2 crackers in the other bucket, and the baby is then allowed to go choose, right? The mother lets the baby go, and the baby crawls. And the question is, does the baby go to the container with more crackers? And the answer is, at 10 and 12 months, these babies can crawl. That's really ceiling performance for a baby. They're 80% correct when the choice is 1 versus 2 and 2 versus 3. They fall to chance at 3 versus 4. Now that's so far consistent with analog magnitude representations, because remember I said that it's strictly a function of ratio, the sensitivity, and we actually know for you that your sensitivity of your analog magnitude representation is 7 to 8. But at this age, it's 2 to 3. So you would expect it to fall apart at 3 versus 4. But this is not the analog magnitude system, because they're also at chance at 3 versus 6, 2 versus 4, and 1 versus 4. Okay? So the limit here is not ratio. It's an absolute set size limit. As soon as one of the sets is more than 3, performance falls to chance. A totally different system of representation than analog magnitudes. Now just dwell on this for a second. 2 versus 3. 1, 2, 1, 2, 3. Babies are way up there, 80% correct. 1, 1, 2, 3, 4, random. Okay? That is really striking, because it's the same number of crackers that you're having to track. There's 5, and you've drawn 4 times as much attention to the bucket with 4 than the bucket with 1, and they're still at chance. Okay, so before we see what system of representation this is, let me show you another piece of convergent data. You show the baby a box into which you can put objects, but the baby can reach into it through a slit, but they can't see. So you show the baby one object, you put it into the box, the baby reaches in and gets that object, and then you measure, do they reach in again? So they've seen one go in, they got one out. If they represented the number of objects in the box, they should be satisfied. Then, on another trial, you put 2 objects into the box, you let them reach in one. It's very easy to do magic tricks on babies. You just surreptitiously remove one from behind the box. And you look and see whether they search for that second one. Okay, and then you reach in and get the second one, having put it back in, and then see if they reach further. And what you get is data like this: 1 in, 1 out. They do reach in again because you're sitting there staring at the box, but they reach cursorily. 2 in and only 1 out. They reach much longer. And then if they put 2 in and gotten 2 out, they're back to the cursory reach. So success on this task is much longer looking when it's expected full than when it's expected empty, either by 1 in, 1 out, 2 in, 2 out. Okay? Here's a success at 1 versus 2. There's 2 versus 4, right? Total failure, just like in the bucket choice task. And here is plotting this as the difference between this bar and the average of those 2 bars. Okay? So success at 1 versus 2, success at 2 versus 3, success at 1 versus 3, utter failure at 1 versus 4. You see 4 things in there, you put them all into the box, the baby reaches in and gets 1, perfectly satisfied. Okay, so the same abject failure as the bucket choice task. Okay, so that's what I just said. All right, what's going on here? They're not using analog magnitude representations here, or they'd be able to distinguish 1 versus 4 easily. Neonates can distinguish in a ratio of 3 to 1 using analog magnitude representations. What they are doing is making a mental model of, it's a working memory model of the actual individuals in the box or the crackers. And so the mental model has one symbol for each individual in a set, right? So these are working memory models. This is a system of representation you have as well. For babies, the limit of a working memory model is 3. For undergraduates, it's 4. For people my age, it's 3 again, right? So again, it's completely continuous through development. This is a system of representation you have as well. And so in this system of representation, there's one symbol for each individual. I think they're iconic symbols for boxes, right? So they're like pictures of boxes with size and color and shape bound to them. Perceptual representations, iconic representations. Notice that in these models, there's no symbol for cardinal values of sets or any other quantifiers. There's just symbols for the individuals. Now, why, therefore, am I talking about this as relevant to number representation? Well, 2 reasons. In order to set up these models, the baby has to be sensitive to numerical identity. They have to know whether that second cracker or that second ball is a different one from the one that already went in there. I mean, different in the sense of same one. There can't be a more numerical concept than that. But also, one of the computations that babies can do on these models, they can represent 2 at once, and they can compare them on the basis of one-to-one correspondence to know whether they've gotten, for example, all the balls that went into that box out. That is quintessentially a numerical computation, right? So in this system, this introduces I think the relevant notion of implicit, or a relevant notion of implicit. In the numerical content of parallel individuation is implicit in the sense that it's carried entirely by computational role, right? There's no symbols for cardinal values in working memory models of small sets. There's only symbols for individuals. And of course, the model of the set, the number of individuals in your model stand in one-to-one correspondence with the number of individuals in the set. That's just because there are rules, they're sensitive to numerical identity, knowing when to open a new object file, right? So it works out that this is tracking number, but not with any symbol for number, okay? So there is a sense of implicit that's really different from, it has nothing to do with accessibility, it has nothing to do with verbalizability. It's saying sometimes the content in a symbolic representation of something that you're representing is carried by the actual symbols in the mind, and sometimes the content is determined, some aspects of the content are determined only by computational role. So the numerical content of parallel individuation, that's the second system, is implicit in this sense. But in that same sense, the A and S symbols are explicit. There's actually analog symbols. What?
Approximate number system, analog number system.
Yeah, A and S, approximate number system, the other one. This one, that system has symbols for cardinal values of sets, although they're analog symbols. Okay? So I've tried to illustrate how you go to work and characterize what a system of representation is like by specifying its format, and I haven't shown you the studies, but both of these systems have been extensively studied in terms of what inferences they support. And I've defined a notion of implicit content, which is some content is provided by the computational role explicit symbols enter into. Okay. So now, let me go back to the issue of discontinuity, right? So I pointed out to you a puzzle. So I just gave you another. These are rich, structured representations. They have a rich computational role with numerical content. Yet, these two are nothing like the explicit symbols that children construct when they learn, for example, a numeralist representation of number. And so once you've got a positive characterization of a core system of knowledge, you can ask, is it discontinuous with a later system? And the way you do it is give that kind of characterization and then give a characterization of your target and look at how they're different. So the characterization of the target here, just very quickly, the first systems of representation that children construct that can represent the content exactly 7 is a verbal count list, where the way it works is it uses the order in a list as a trick to specify which cardinal value that you're doing. So you count 1, 2, 3, 4, 5, 6, 7. Okay, 7 refers to sets of 7. It's the 7th item in the list. And once you've figured out that representational system, which is a culturally constructed one over centuries, right? Then the child has to construct something entirely new in order to master that, and they then have a representational system that with more expressive power than anything that they had innately. So the discontinuity here, you have, the point is that system at least represents a finite subset of natural number. These two systems can't represent natural number, right? Obviously, the parallel individuation has no symbol for integers and a set size limit of 3 or 4, but the analog number system can't represent exactly 5 or 15 or 32, right? It can only represent approximately. And furthermore, it obscures the successor relation because numbers are compared by their ratios and not by their average difference. They can't even resolve the difference between 9 and 10, right? So neither of these, in principle, can represent integers. So this has the consequence that learning to count should be hard and should not be cross-culturally universal. That not all cultures should have representations of natural number, and both consequences are true. And I'm not going to show you that data or characterize the learning mechanism I think that achieves this difference. I just wanted to illustrate that probably one answer to why the solidity constraint can't be answered explicitly is that it's probably implicit internal to the module. It's it's a constraint on the predictions you make, and it takes a bit of theory development to become explicitly aware of the solidity constraint. And probably, we don't know, that's true for the theory of mind discontinuity as well. So I think, but we don't know that in those cases because we don't have positive characterization of what the representations are like. And that's what I want to turn to now. So the gap between core cognition and later explicit linguistic representations is not simply a function of core cognitions itself being implicit knowledge. There's explicit symbols in the core cognition. The ANS explicit, in the sense I just said. The PI, this should say implicit. This one is explicit in the sense of guiding behavior, right? Parallel individuation is guiding how many times you reach into the box, right? So it's explicit in that sense. It's just that the numerical content is implicit in the sense of not carried by explicit symbols. But neither of these are capable of expressing the meanings of verbal numerals, and that's probably the reason for the fact that it's very hard for preschoolers to master these representations. Okay, I want to end with 20 minutes on the question of whether infants have a logic-like language of thought, right? So the fact that there are the innate primitives include sensory, motor, and perceptual representations. They include these systems of core cognition, which are they have highly abstract content, rich conceptual role, but otherwise might be perception-like, right? This is the question, right? So these are examples that I quickly. But the existence of innate primitives like this does not preclude also the existence of a central language of thought that's logic-like, right? It's an empirical question. So is there a Fodorian language of thought that non-human animals have and infants have? Eric was arguing yes. So we need a characterization of what we're talking about. So for sure, there's going to be an issue of format. The symbols should be arbitrary, discrete symbols, like letters for variables. There should be the right kind of combinatorial productivity, supporting logic and logic-like syntax. These representations should have the possibility of expressing propositional content, and they should support deductive inference. Okay, so the question is, do babies and animals have this? Right? They clearly have abstract representations, structured representations. That's what I just gave you evidence for. All of the systems of core cognition I just described, non-human animals have as well. Okay, Fodor answers, obviously, yes. What allows for central conceptual role if there isn't a central language of thought? His arguments about productivity and systematicity. And also, this is an argument I find compelling, we humans clearly have a representational system of that sort because we have language, and language paradigmatically is like a Fodorian language of thought. So how could language be learned if we don't already have the capacity for those kinds of representations? Other people have argued, obviously, no. The first, I think, explicit argument about this is from Descartes, and that's because Descartes invented the computational theory of mind as it applies to perception. I mean, he is so prescient in his theory of perception. He just got it right. He just nailed it. And so since he saw perception as a computational process, he asks, but are the computations in perception like those in thought? And he argues no. He says they are. You need a natural language for thought, and so Davidson argues you need a natural language for thought. Now, there's two versions of this hypothesis. I certainly believe there has to be innate support for abstract thought for us humans, because I accept the argument that how else are we going to learn it, right? But you could still deny nonverbal creatures a Fodorian language of thought, I think, in two sensible ways. One is you think, well, maybe this kind of thought arises in hominid evolution with language, co-evolves with language, and it arises in ontogenesis only upon learning language. So the innate support is part of what supports learning language. That's a sensible possibility. Or another possibility is it's present in non-linguistic creatures, both babies and animals, but it's implicit in the sense of carried by the computations that explicit symbols enter into. Okay? Those are two sensible hypotheses. This would say there's no symbols for if, and, or, not, same, different abstract representations that can articulate proposition-like sentences that babies can represent, but there's logical content given by the computations that explicit symbols enter into. Look, what we need here is a characterization of what perception is like, and maybe core cognition on the one hand, and what thought is like on the other hand, to even engage this question. And I don't have time because I want to actually show you some data that counters Eric's guesses. But here is one. If you've not read Tyler Burge's book, or he's got a short paper on just this question that was published in a Portuguese journal called Disputatio, which is very clear, in which he tries to characterize the kind of logic that and kind of productivity that perception allows, and contrast it with that of what he calls true thought, true predication. So this is a kind of pseudo-predication. And I'm not going to go through this, but the point is, to even engage this question, you need to give this kind of analysis, right? So there's Burgess. So the photocentral non-modular processes versus modular processes is one attempt to draw this distinction. It's different from Burgess' true predicates versus perceptual attributive distinction. There's Newell's physical symbol systems versus distributive connectionist system. That's another way of trying to characterize a joint in nature between perception-like combinatorial productivity and true logic-like. Gendler's A-leafs versus B-leafs. This is not something I'd ever heard about till this conference. Descartes' true thought versus perceptual computations. Davidson, Bermudez, Camp, Carruthers. Lots of people have given these analyses. And so part of the project, this is the project that I'm working on now, and I think there's probably many distinctions here. There may be many kind distinctions, and how they are going to fall out, I don't know. But what I want to rather say is, once you've got one in mind, how do you find out whether animals or babies have representations of that nature? Okay? So here's the research strategy. You have to do exactly what you did for number. You have to find a face valid task that might reflect the content in question. So for number, it was habituation to sets of dots that shared a number, or the reaching into the box, or the cracker choice tasks. Then you have to rule out deflationary alternatives. If babies succeed, are they succeeding on the basis of some property of those arrays that's not number, right? So you have to rule out that they're actually sensitive to number and not total spatial extent or the duration of the event to happen, and all of those controls are done in these experiments. Then you go to work to constrain the models of format and conceptual role by exploring distinctive signatures of different formats and conceptual roles. So that's why I went through the number case, and that's, I assume, why I sent the title in here of Core Cognition of Number. What I had in mind, I don't know. Okay, so I'm going to race through two examples. So the first case study is logical connectives, because even though I don't have a good analysis of how perceptual representations differ from logic-like ones, if you can show that babies can think a thought, this is not an elephant. There is no way that there is any kind of representation that underlies that thought that isn't on the Fodorian language of thought. So we chose or and not, and the disjunctive syllogism, because it's a deductive inference to explore this. And the other reason we did this is because there's an animal literature on the disjunctive syllogism. And the animal literature thinks that animals are capable of logic because they can work through a disjunctive syllogism. So the first thing we wanted to see, can babies do what animals do? So the task with animals is very simple. You have two containers. You bait one of the containers behind a barrier. So you put something in one of the containers. You show that the animals can't tell by smell or anything else which it is, because if you just give them that choice at that point, they choose randomly. Then you show them that one of the containers is empty. The question is, do they go to the other container without looking, right? So is it A or B? Not A, therefore B. So can they do this? So Joseph Call did this first with 4 species of primates, and all species of primates, 3 great apes and I think gibbons. Some of the individuals, after quite a bit of training, managed this. So it's in the competence of all his great apes. Since then, I love the animal cognition literature. It's been done on about 40 other species, exactly the same task, right? And the answer is essentially the same in crows and dogs and all kinds of primates, and I don't know what other ones, ravens, smart animals, a parrot. It's in the repertoire of at least some individuals in all these species, but it takes quite a bit of training, and not like 1 out of 8 can do it, or 7 out of 8 can do it. So it's not trivial. Okay, so so the first thing we did, this is a face valid task. I want to see, can babies do it? This is Shilpa Modi, who is the person whose work I'm reporting here. And I just show you the version we did.
Okay, ready? It's going. Kevin, look at this. Okay, where's the duck? Can you find the duck? Yeah, there he is.
Okay, all right. So that was a 23-month-old. They get it right on the first trial. There's no learning over time. And it is, I'll show you the data. 23-month-olds robustly succeeded, but 14 and 17-month-olds failed. Okay. Now, so this is just a first exploration, and we want to know, first, does that success mean they're working through a disjunctive syllogism? But secondly, we want to rule out deflationary alternatives of both the success and the failure. Maybe the younger children failed on this because all we did was draw their attention to the empty one. And so what they have to do to succeed is disinhibit. You know, they both remember, this is some substantial working executive function demands for kids this age. So they have to remember that there's a ball there and remember it through the showing them the empty one, but then they have to disengage their attention on the empty one. So we tried to decrease the inhibition aspect of this in a very simple way, which I'll just show you. This is a 15-month-old.
Oh, are you ready? Get the bird going. Okay, now look at this. And look at this. All right, where's the ball? Can you find the ball? Oh, where's the ball?
Okay. So now 17-month-olds succeed. So there was some executive function demands of this task, and it doesn't matter, we counterbalance whether we show them the empty one first or we just raise the other one first. That doesn't make any difference at all. But just touching both of them gets the 17-month-olds to succeed. But 15-month-olds are still objectively failing. Now, this could be because this is still an executive function demanding task. So we want to rule out some simple alternative explanations here. Is it that they just forgot that there was a ball there, or maybe not motivated to get the ball? You know, they see it hidden, and then you take this down, and then you do this weird thing of turning one over and raising one up, and they maybe just lose you altogether there. So we want to rule out that alternative. So we did one more version, and I'm going to show it to you, but the difference here is she separates her hand before she puts it down. So they don't have to infer where it is. They just have to follow where it is. And then, but then she takes it down and does all the extra stuff. So if they're just forgetting or being confused by all the intervening stuff, they should fail. Okay, so.
Okay, you ready? Look where it's going. Okay, look at this. And look at this. Where's the dog? Can you find the dog?
Okay, so that's a 15-month-old, and now they're succeeding. Okay, so here is the interim summary here. What's entirely open here is whether what changes between 15 or 17 months is change in irrelevant reasoning ability, representation of negation perhaps, computations involving negation, or rather just changes in the information processing capacity that allows the demonstration of this representational capacity in 17-month-olds, but not 15-month-olds. That would be a deflationary alternative with respect to what we're trying to see here, okay? So how are we going to bring data to bear deciding between these alternatives? Well, we look for domain generality of the developmental pattern. So let's look at lots of other cases where the disjunctive syllogism or negation is involved and see whether we can find evidence for it in 15-month-olds where we're not finding it here. So one is mutual exclusivity in the word learning situation. So if you say to the child, look at the DAX, or where's the DAX? By 17 months, babies look at this, all right? So the idea is the DAX is either that one or that one. It can't be that one because that's called a cup. Therefore, it must be that one. So that's why this is supposed to be the disjunctive syllogism. You want to show what you're going to do is measure looking time. You want to show that they can do it if you say, where's the cup, right? So that their eyes show this. And this just shows that they can from 14 months on. This is the percent of looking at the cup, at the correct one, relative to the baseline preference for those two. And you see it's just constant over this. I mean, it's noisy, but they're systematically looking at the cup when you say look at the cup. But what about look at the DAX? Where's the DAX? Success at 17 months, the same as in our other thing. Abject failure at 14, 15 months. Random at 16 months. Okay, so the same developmental change. Now this is totally different information processing demands than the working memory executive function demands in the other one. Okay, and I had a whole second case, but I'm not going to do it. It's too bad. Shit. So let's go back to core cognition of agency. Okay, so we know that babies are representing goals and epistemic states and perceptual states and self-generated emotion. So what's the format of representation here? Is it Lewis's Ramsey sentence representational format? Not likely, but maybe. Is it even logic-like or language-like? Do they have a schema like ARB, where R is some relation like that can be plugged in with wants, so they can think, mommy wants coffee, I want to go to the playground, etc. Okay? If that's so, you might think it would compose, this kind of representation could compose with not if they had a symbol for not. Okay? So let's see whether they do. So I remember I told you that babies actually represent preferences in this circumstance, not just goals. So we did an experiment where on successive trials during familiarization, the hand is always in one condition reaching for the ball, okay? So ball, ball, ball. But the other thing is changing on each trial. So ball over A, B, C, D, E, F, G until the child gets bored, okay? But there's another condition where what the hand is always reaching for is not the ball, okay? So reaching for A, B, C, D, E, F, G, and the proper generalization is he doesn't like the ball, or he doesn't want the ball, or anything but the ball, not the ball, right? So can the child do both of these? So we tried it first with 7-month-olds who can easily do the basic he wants X. And so this is just getting bored during that period where they're reaching all the time for the ball in this case, or for the not ball in that case.
What do the numbers mean?
I'm going to show you. This is the amount of time they look during the familiarization trials. These are the first 3. This is after they've reached the habituation criterion. And then this is the case the very first time you show them something that breaks the pattern. So they've reached ball, 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 ball. The very first time you now give them X and Y, where they've never seen Y, but you reach for Y instead of X, the babies look longer. So they could indeed represent he wants the ball compared to anything else, and they're therefore surprised when they reach something else. But here's the case where they're reaching for the not ball. Absolutely not, they're not at all surprised the very first time they reach for the ball, right? So they haven't represented, he doesn't want the ball. In the very same circumstance that it's easy for them with exactly the same kind of evidence to represent, he does want the ball. So that was 7-month-olds, so we decided, okay, well, let's go up to 14-month-olds, which is the age at which they're still failing these other destructive syllogism stuff. So maybe they can integrate their representations of agency with some representation of negation. We asked adults to describe what you're seeing, and adults look at, the first 3 alone, and they say, doesn't like the ball, doesn't want the ball, reaching for anything but the ball. I mean, it's totally obvious. Again, 14-month-olds are entirely failing. Now, we haven't done the 17-month-olds. But if the 17-month-olds succeed at this, then we will say, okay, by that time they have a representation of both negation and a representation of these goals that can be integrated with negation. I don't know what will happen, but if that pattern still continues, 14 months absolute failure to see any sign of negation here, I had another one where they can represent same but not different as not same ages, right? Is suggesting that the format of representation that is underlying the success on these core cognitions is not in a format that combines with negation, or maybe they don't have a negation operator that can articulate working memory representations at this point, right? Okay. The failure to carry out a negation computation under 15 months in 3 different tasks with vastly different information processing demands, and the 4th was same and different that came below. There is a failure, and if the success at all of these emerges around the same age, this suggests perhaps that there's some change in capacity to represent negation per se. What are they learning at this age? They're learning to express negation in language. It's not clear that that there's a domain general explicit symbol for negation is needed, though, in the computations underlying success, even if you have success. It could be all done in terms of positive representations for the baby, like a void, empty novel. And I'm just going to close. I'm sorry I don't get to do the same different stuff, but I want to close with this question. 17-month-olds and 23-month-olds are robustly succeeding on this task. But does that mean they're working through a disjunctive syllogism, right? If they are failing, they clearly aren't. But are they? So what representational alternative is there? And what might some signature of deciding between the 2 alternatives be? Well, there's an alternative, which is, this is a search task after all. If you're searching, it's really stupid to go search in a place that you've just seen as empty. So they're avoiding the empty bucket, perhaps, but maybe when they see the empty bucket, they're not actually updating the representation of A to it being 100%. So the signature you want is deductive certainty. Now, people have looked for deductive certainty in both 2.5-year-olds and chimpanzees in the following way. There's 3 tubes, and you can look into them and find a peanut in one of them. So the chimpanzee, of course, has no information. So looks in one, looks there, looks in the second one. Not one in the first one, not one in the second one. The question is, does the chimpanzee look in the third one or just go reach in the third one? Because actually, when they reach, they're not looking, right? So they're just reaching in and get it. And the people who did that experiment say, oh, yes, wonderful. They do that 7% of the time. I say, 7% of the time? And that's the same with 2.5-year-olds. They also do it 7% of the time. When do they do it reliably? Age 5. So age 5, they just reach for it. Okay. Now, we did an experiment that gives, I think, really strong evidence that by age 3, children are working through a disjunctive syllogism. I'll just describe it. So we have two sets of cups, A, B, C, D. We hide a sticker in one of A or B, hidden. We hide a sticker in one of C or D. We then show them that C, as it were, is empty. And then the child gets to choose. So if they've worked through a disjunctive syllogism, they now have a representation that one of those cups is certain to have a sticker and the other pair is 50-50. So we can distinguish deductive certainty from a strategy, avoid the empty one. 2.5-year-olds search 33%, 33%, 33%. They are avoiding the empty one. 3-year-olds and up go to the deductive certainty one. So the story that I'm just going to go to my concluding slides and then stop. It's to show how much I completely overestimated what you could do. Overall conclusions. What are my overall conclusions? I distinguish two senses of implicit and explicit. One concerns access and central conceptual role. Another concerns whether the content is carried by a mental symbol or by a computational role as well. And I argued that the gap between infant core cognition and later verbal cognition is not entirely explainable by core cognitions being implicit. And I question the idea that logic is part of basic cognitive architecture in the sense of easily diagnosable in non-linguistic thought. So, thanks.